Alright, this is 3.2. So in the last video, we told you that light behaves like a wave, right? But in the unit immediately after that, they tell you that light is a particle. Well, it demonstrates particle-like properties. So which one is it? Is it a wave or a particle? Well, the real answer is it's a bit of both. What that really means is, in some experiments, such as the Young's double slit experiment, light behaves like a wave, right? It diffracts, they constructively and deconstructively interfere to form bright fringes and dark spots on the wall. But in the experiments we're going to talk about today, light behaves like a particle. Now, the first thing is photoelectric effect. It's a phenomenon where if you, let's say, shine light, uh, if you shine a ray of light on a metallic surface, yellow for light, like that, right? The electrons in this metal are gonna be freed. They're gonna be freed from the surface, and they are gonna be lost from the metal. So basically, they're ionized, right? They escape the metal to go somewhere else. And for this one, we need an equation that is E equals HF. This equation basically states the energy of a photon is the Planck's constant times its frequency, so how fast it's vibrating. And we can visually represent this using three arrows. So if I go all the way back and get us some new electrons, that's bad. That's good. So we have a ray of light coming in, right? We draw an arrow like this. Actually, an arrow like this. And the electrons are freed, but before they're not just immediately freed from the metal. Some energy of this photon goes to freeing the electron from the surface, right? It raises the electron to the surface, just to the surface, and the rest of the energy from there on goes to the kinetic energy of this emitted electron. So, if this energy is used to free, let's say, this electron in particular, then this much energy, right, is needed to rise the electron to the surface. And from there on, the rest of the energy is its kinetic energy. So when these two combine, they have the same length as the first arrow we draw here. But let's break down what this means. So we already know this is the kinetic energy of the emitted electron, and this is what we call the work function. And then here we have the energy of the incoming photon. So I'm just gonna say E. But what we are interested in is the maximum frequency. And when you think about it, since E equals HF, the maximum frequency is produced by the maximum energy electron. So the electron with the maximum kinetic energy will be the one that has the longest kinetic energy arrow, right? That means it will have the shortest work function arrow. But that means it is the least bound electron out of all the other electrons in the metal surface. So it will be the one that's, well, closest to the surface. In this case, it will be this one. So here we get the work function, which is defined as the amount of energy required to free the least bound electron to yeah, to rise it to the surface. And then the rest of the energy is the kinetic energy, and this will be at EK max, the maximum kinetic energy. And with these three arrows, we can draw up a conclusion, an equation. So E equals EK max plus W. So we can have the energy of a photon is equal to EK max plus W. And we know the energy of a photon is just given by H times F. So same thing, EK max plus W. And then with some simple rearranging, we just get what we have on the formula sheet. EK max equals HF minus W. So that's how you get this equation, and you'll be required to be able to derive this one in exams. Now, secondly, we're going to talk about X-ray and how they are produced. So, since the invention of X-ray, we only have found just one practical way of producing X-ray. All the X-ray machines you see in the hospital use this pretty simple but energy wasting method of producing X-ray. It's actually pretty primitive and essentially uses the same method as when the first X-ray was produced. So this is how X-ray is produced, basically. You have a filament, and on the other side you have a target. And in between, there's a potential difference in between. So this will be the positive end, and that will be the negative end. Now, some current will be running through the filament. And when there's current, there's charged particles. So electrons are gonna be emitted from the filament, right? They're gonna be emitted and they're gonna come out. And since this is the negative end and there's a positive end, you will go towards the positive end straight to the target. And when it collides with the target, the collision produces X-ray photons. But what is really happening on a micro level is we can draw it out like um, so you have a nucleus. And then you have the electron levels, right? You have the electron levels. 1, 2, and then 3. All right, perfect. Now, an electron could come in like this, misses everything, not actually come into contact with anything, but, right, it misses everything. It's not touching anything, but it still gets decelerated by the nucleus, just like a satellite going around a planet, right? In this case, it is decelerated, and it loses some of its kinetic energy. Thus, the process will release a X-ray photon with the same kinetic energy as the energy lost here by the electron. But you can also have electrons that come in and just hit the nucleus. In this case, the electron will be completely stopped. It loses all of its kinetic energy. So what do we get? We get a X-ray photon, right? We get an X-ray photon emitted out of here with all of that kinetic energy from the initial electron. So that's the energy, and this one will have equal energy. And we can calculate the energy of the electron just by using E equals, well, W equals QV. W equals Q times potential difference. And we can um, write it like this because it's electron, right? So this here, we're, oh, crap. That's the eraser. Okay, there you go. So what you really have is E V, and this here will be the maximum kinetic energy of an X-ray photon. So we can write an equation. EV equals EK max. But we can break this down furthermore. What's the how is the energy of a photon calculated? Well, H times F, right? So we can write this out as H times F max. And same thing on this side, E times V equals that. Some simple rearranging. F max equals E times V over H. And this here is what you see on the formula sheet.